Okay, thank you very much. Thank you very much for giving me the opportunity to present our work in this seminar series. So I'm going to talk about the effect of the lattice in general on nematic quantum criticality, taking the example of sulfur-doped iron selenide. The work I'm going to be presenting is essentially based on the thesis of this PhD student Soumeya Shibani. And if I have time at the end of my talk, I will also talk about some recent elasto-Raman measurements that was a core of the PhD thesis of Jean-Côme Philippe. So we enjoy some theory input from Indranil Paul in our university, and samples were provided by different groups, especially in Japan, France, and Germany and the US. So just a reminder that I think most of you know the phase diagram of iron-based superconductors. So the question I'm going to address is relatively simple. So we all know that superconductivity tends to be enhanced at the termination point of essentially two phase transitions. One that involves magnetic ordering, stripe-like antiferromagnetic order, and the other one is the so-called nematic phase, where the system breaks the C4 rotational symmetry of the iron lattice. So what I'm going to address is which, if any, of these so-called critical fluctuations play a role in enhancing TC. And of course, one of the difficulties in many of these iron-based systems is that both critical points associated with magnetic order and nematic order usually coincide. So this is the case of baryon 122, where if they do not coincide, they are very closely following each other, which makes it difficult to disentangle their role in boosting TC. So I'm going to be mostly addressing the role of nematic quantum criticality, and there are actually several work, theoretical work, that appear in the last, let's say, 6 or 7 years that have argued that generically you expect the TC to be enhanced at the nematic quantum critical point, and this is sort of irrespective of what is the main pairing mechanism away from the QCP. So even if it's, let's say, a phonon-driven superconductor, it would still be have its TC enhanced at the nematic quantum critical point. So this is a generic effect that is seen in these theoretical models, both in the case in the context of cuprates or in the context of a more general, let's say, nematic quantum critical point. Now, one important aspect that is sort of not included in this model and that is going to play a role is that lattice effects are ignored. Now, one nice playground to study this effect is iron selenide, because as most of you know, if you look at this phase diagram, for example, as a function of sulfur substitution, it has a superconducting phase at a relatively low TC, below 10 K. And it has a nematic phase in blue, but there is no magnetic order. So it's sort of a plain vanilla version of a nematic QCP, where you have when you introduce sulfur instead of selenium, you continuously weaken your nematic phase up down to some critical point. And one of the puzzles that you immediately see in this phase diagram is that if you look closely at the evolution of TC in the red dots, TC seems to be hardly affected by the QCP, and if anything, it's actually decreased. So this is a puzzle from the point of view of this theoretical expectation. So one way to look at this effect of quantum criticality in the nematic channel in this phase diagram is to associate it susceptibilities. This can be done, for example, by elastoresistivity or shear modulus measurements if you are thinking about the lattice. But what I'm going to show you is work that is based on an optical spectroscopy, electronic Raman scattering, that is dedicated to study these Q=0 fluctuations. So Raman scattering is a photon-in, photon-out technique. So it's essentially inelastic scattering of light. And typically people use this tool to study optical phonons. So this is a typical Raman spectrum of iron selenide at room temperature. So you see the sharp peak at relatively low energy, that's an optical phonon. But that's not what I'm going to be mainly interested in this talk. What I'm going to be interested is the continuum that lies below the phonon. And this continuum is due to essentially particle-Hall pair. It's of electronic origin. So how to understand this continuum? So one way to see this continuum is that it corresponds to a dynamic charge fluctuation in the uniform limit, so in the Q equals 0 limit, because the photon that we are using are visible photons. So their wave vector is very small with respect to, let's say, typical wave vector in crystal, like the Brillouin boundary or the Fermi energy. So what we are essentially probing is a density-density correlation function, but this is not just the usual electron density. It's a density that is dressed by a vertex that I would call gamma, that is sometimes called the Raman vertex. And the K dependence of, so this is not an isotropic object. In that case, that would just be the electron density. But this has a K-space structure. And this K-space structure is actually dictated both by symmetry, mu, and light polarizations. So by using different light polarization for photon in and photon out, we can access different values for this vertex. So let me give you an example, and I will take the example of the D4H point group, which corresponds to, let's say, the high temperature point group of the iron-based superconductors. So in that case, you can decompose it into different irreducible representations. So B1G, B2G, A1G, A2G, and GM. I'm going to be interested mostly in the first three. I'm going to illustrate sort of the K-space structure of these components, first by starting with the B1G. So here I'm going to use throughout all my talk the one iron unit cell representation. So the B1G will correspond to the nematic order parameter symmetry. So if you use the 2 iron unit cell, you would have to interpret B1G and B2G. But I'm going to use the 1FA unit cell in my talk. So this would correspond to, if you think about the electronic subsystem, to a distortion of the Fermi surface, where you would shrink along the one axis and expand it along the other axis. So that's precisely the symmetry of the nematic order parameter that is seen in iron-based superconductor, at least in most of them. So you can also think about the B2G symmetry. And in that case, that would be the same kind of distortion, but rotated by 45. The A1G is the fully symmetric channel, so there is no associated breaking of symmetry associated. So thanks to this sort of symmetry selective aspect, Raman is a natural probe of Q equals 0 instabilities of Fermi surfaces in general. So in the specific case of iron-based superconductors, we are going to be mostly interested, of course, in the channel, in the B1D channel, where nematic fluctuations are expected to appear. So let me first show you the typical Raman spectrum in iron, starting with pure iron cyanide. So pure iron cyanide has a TS, a nematic phase transition of 90K. And this is the spectra, the Raman spectra, as a function of temperature in the tetragonal phase, so above 90K, in this B1G symmetry that is obtained by using this cross-polarization configuration at 45 degrees of the iron-iron bonds. So you see that there is a considerable temperature dependence in the above TS. But what I'm going to be interested is mostly in the low energy component, which I'm highlighting here in red. You see that there is a relatively sharp quasi-elastic emerging close to the transition. But I should note that there is also a broader and less defined broader peak at high energy, here highlighted in green. So there is a two-component response in this B1G channel. And if I look at the other symmetric channel, let's say B2G and A1G here on the right, you see that the equivalent spectra as a function of temperature do not show much structure. I mean, there are sharp peaks at low energy that are due to optical phonons, but if you just concentrate on the continuum, it's relatively obvious that there is much less temperature dependence and much less structure. So most of the action takes place in this nematic channel. So I'm going to be mostly concentrating during this talk on the low energy part. If you want, we can discuss also the broad peak here highlighted in green. So focusing on this low energy part, this is sort of the low energy part of the spectra as a function of temperature on the left above TC and on the right below TC. So you see that there is an increase at low frequency down to the nematic transition temperature. And when you cool down below TS, there is a collapse of intensity. So this is sort of this quasi-elastic peak is sort of a signature, if you want, of critical fluctuations that are developing upon approaching TS and collapsing once you enter the order phase. So sort of the simplest way to analyze this kind of dynamic fluctuation, so the imaginary part of the response as a function of frequency, is to convert it into a static susceptibility. So this can be done by using a Raman-Scattering transformation. So essentially integrating chi double prime of omega over omega up to high frequency, up to essentially a cutoff where the spectra are no longer temperature dependent. So it's essentially integrating this quantity here I'm showing on the left. So if you do that as a function of symmetry, this is what you obtain on the right. So you have a static susceptibility that is resolved in symmetry. So you can do the same operation in all the different irreducible representations. So in red, you see B1G, which follows approximately Curie-Lattice-like behavior. And in purple and blue, you see the other symmetry where it's essentially flat and featured. So the one important aspect of this Curie-Lattice dependence is that even though the susceptibility peaks at TS, clearly, the Curie-Lattice temperature is actually located at lower energy T node. So there is a distinction between TS and T node. So this is a sort of the same distinction for people who are used to elastoresistivity, but maybe for the people who are not familiar to this, let me explain briefly what the difference between these two temperatures means. So essentially, the difference between these two temperatures is an effect of the coupling to the lattice, so what is known as Nematic coupling. So one way to think about it is to use the lambda of free energy, where you would have the epsilon, which is the lattice orthorhombicity, and psi, which is the Nematic order parameter. And since they belong both to the B1G representation, they have a bilinear coupling. And this bilinear coupling is this last term, which has a coefficient lambda node, which is often called the Pneumatic coupling. So let me, since there is now consensus that this transition is really electronic driven, but one can have a model where the bare nematic susceptibility, so the electronic nematic susceptibility, 1 over chi B1G, which is the one that is posed by Raman, is going to follow Curie-Lattice like dependence. So 1 over chi is proportional to T minus T node. And if you do that, you will see that the shear modulus CS node gets renormalized to CS by the following formula. And this actually goes to 0 at a transition temperature that is higher than TS. And of course, the transition at which the renormalized shear modulus vanishes is the true thermodynamic transition, TS. Whereas T node, which is located at lower temperature, if you want, is the fictitious electron-only nematic transition temperature. It's the transition temperature at which the system would transit if there was no lattice. And the coupling to the lattice actually stabilizes it to a higher temperature. So the difference between the two transition temperature, TS and T node, is set essentially by the square of the Nemato-elastic coupling. Okay, that said, what happens when you dope with sulfur? So this is the evolution.
Do you mind if I ask a question at this point? Is there some estimate of this? Maybe this for both you and Zhonghao. Is there an estimate of this T naught parameter from, say, elastoresistivity?
Yeah, so this I'm going to show you for in the case of Raman. So for pure iron selenide, there are at least 3 or 4 different measurements of elastoresistivity, and they would broadly they would range from I think 30K to 50K.
Okay.
So significantly below TS, but there is some scattering.
Mm-hmm. Okay, thank you.
Yeah, I actually also just pull out the data from my group. It's 34 Kelvin. So
34.
Yes.
Okay, so let me look at the evolution of this nematic fluctuation spectrum as a function of sulfur. So those are the data, again, at low energy, focusing on this quasi-elastic peak as a function of sulfur in the sort of the low sulfur concentration part. So you can see in all this concentration an increase upon lowering temperature. And once you cross TS, which is finite in these 3 samples, there is a collapse. So the evolution is consistent with the one found for pure iron cyanide. And if you further doped, so you enter composition at which no structural transition is seen, essentially the spectra show the development of this quasi-elastic peak down to the lowest temperature. Note that in the highest concentration, so 27%, this enhancement is significantly reduced. So there is already signal at this sulfur composition that the nematic fluctuation starts to have to decrease significantly. So one way to analyze the data is again do sort of the integral of this dynamical spectrum and extract the static susceptibility and fill it with a plurivalence-like behavior, and that allows us to extract a T-node. So this can be done in different ways, but here I'm showing you two different ways. One is by fitting essentially the low energy part with a quasi-elastic peak and extracting the susceptibility from it, or a direct integration of the low energy. And this is the result on the phase diagram on the right, where you essentially the open and filled symbol represent different determination of this T-node. And what is, I think, relatively striking is that even though there is some scatter in the point, it's pretty clear that there is a shift between the doping where T-node extrapolate to 0 and the doping where TS extrapolate to 0. So if you want, there is a significant shift in terms of sulfur composition between the thermodynamic QCP and the bare QCP that would happen where there was no coupling to the lattice. So of course, sulfur doping is not really a correct way of thinking and comparing things because it's a bit arbitrary. So one would like to have some kind of dimensionless parameter to sort of quantify this lattice shift. So one way to do that is to use TS minus T node as a Nematic energy scale and renormalize it to an energy scale of the electrons, and that would be in our case the Fermi energy. So in that case, the phase diagram that you would get would be T versus this dimensionless parameter, and the shift R node would be precisely this parameter. So that's sort of a way to quantify the shift, and of course, this shift has to happen because if you think about it, it's an unavoidable consequence of the fact that TS and T node are different, and therefore their associated QCP have to be different. So this is the result. This is this coefficient as a function of TS, and the shift here is indicated by the arrow. So if there was no coupling to the lattice, so if the Nemato-elastic coupling constant was 0, essentially, the QCP would be at the origin of this graph, right? When TS would go to 0, R0 would be 0. And here you see that there is a relatively significant shift, and with a value of R0 of about 0.3. Now, what is the consequence of this significant Nemato-elastic coupling? So this is a work that was actually done by my colleague Ranil Paul. So one of the main effects of this coupling is that it's essentially cutting off the nematic fluctuation. And the consequence of the cutting off of this nematic fluctuation by Gallais is that there is going to be a big impact on the superconducting pairing actually. So essentially, what they found is that you have two regimes. One regime is where this R node, so this lattice shift is small. So in that case, you expect a strong enhancement. So you are essentially in the electron-only limit, where all the other calculations are valid. But if there is a strong electron-lattice coupling, so typically if R0 is on the order of 1, the enhancement is essentially 0. So this scenario sort of seems to provide, at least qualitatively, an explanation for the weak enhancement or the absence of enhancement in sulfur doped iron selenide. And in that case, the location of the bare QCP seems to be the key to the behavior of TC. And in iron selenide, this shift is a significant, as indicated by the R0, and so that we are essentially in the weak enhancement. So in that case, what seems to be the sort of the takeaway message of this would be that superconductivity is essentially set by most likely spin fluctuations. And they have a different character above and below the critical point that would explain the difference in TC above. Okay, so I don't know how much time do I have left.
So we would like to have 10 minutes discussions, but no, if you can try to finish in 5 minutes, that would be great.
2 minutes, because it's nice. So just recently about this Nematic coupling, there is this elastocaloric effect coming from the group of Yann Fischer, where they saw a huge decrease of this elastocaloric effect in cobalt barium 122. And this collapse was actually attributed to a collapse of the Pneumatoelastic coupling upon approaching the critical doping. So the idea is that if I here look at my plot of R node, the blue point are now the data point coming from our data in cobalt barium 122. So what I was doing before was sort of doing an extrapolation down to the critical point. So is it possible that in fact this coupling will go to zero at the critical point? So let me just very briefly show you that one way to address this problem is to do elasto-Raman. So we recently built a setup combining symmetry resolved Raman scattering with uniaxial strain. So this sort of allows us, in the specific case of this matter, to probe the nematic susceptibility under a symmetry breaking field. So let me just briefly show you this. So this is an example of barium 122 under uniaxial strain close to TS. And you see that both under tensile and compressive strain, there is a decrease of the low energy quasi-elastic peak. And this decrease can be converted into a change of nematic susceptibility. So this is the plot here I am showing you. So the orange point are the change in nematic susceptibility as a function of both compressive and tensile strain. And the important thing is that you can have a relatively simple expression of this reduction of nematic susceptibility under a symmetry breaking field, and you expect it to essentially scale. This is one of the equations at the bottom as lambda square and the susceptibility to the cube. And indeed, when you go away from the phase transition temperature, nematic susceptibility decreases and the effect is dimensionless. Now, the key point I wanted to mention is that you can do actually the same kind of measurement in a superconducting composition. So in a sample where TC is 24K, so very close to optimal doping. So this is the data on the right, where I plot delta chi node over chi node for both doping. And what is immediate, so this is the same scale in terms of the B1G strain. And what you see is that the data, even in the superconducting state at 9K, that's in purple, they seem to be very similar to the one at 0% close to TS. And in fact, plotting them as a function of epsilon square, which is the behavior, you have a slope that is very similar between both compositions. So since chi node is essentially very similar from Raman measurement under no uniaxial strain in these two kinds of composition, that sort of indicate that a collapse of this lambda square is unlikely unless there is a huge enhancement of the quartic term. So from the point of view of these elasto-Raman measurements, there seems to indicate that the Pneumatoelastic coupling does not change so much. Okay, let me finish with this. So what I showed you is that there are significant nematic fluctuations throughout the sulfur doped ion signal phase diagram. I think the key take-home message is that coupling to the lattice is important, and it's probably affecting the TC enhancement at the nematic QCP of the system. And I showed you that elasto-Raman measurements on barium 122 seems to indicate that there is still robust Pneumatoelastic coupling down to the QCP, at least in cobalt barium 122. And I thank you very much for your attention.
Thank you, Yann, for this beautiful talk. So let me take advantage as a chair comment, which is I'm very happy to actually see your results of applying strain on Raman and actually see the decrease of nematic susceptibility. As you know, we have a recent work on using strain to suppress superconductivity. I know one of the puzzling things want to know is whether the strength actually suppress pneumatic fluctuation. But at least from your data, it looks like it is the case.
Yeah,
and
what is quite striking also is that the suppression seems to be almost identical right above TC and well below TC.
I see. Right, and then yeah, I guess a quick question is that what is the U here? And then
so U in the Ginzburg in the Landau, sorry, the Landau picture is the quartic term. So that's would be the U of the psi4. So when you have your Landau expansion, you have.
I see. Okay, the higher order term coefficient.
So yeah, so of course not much is known about this. So I think one would have to do more like a microscopic calculation to really.
Yeah, I think it depends on how we actually define the pneumatic order parameter, right? Because eventually that coefficient multiplied order parameter square will be, or the power of 4 will be the free energy. So at the end, it has to convert to the unit of energy. So, okay, I see a hands raised by Amir Abbas. Please go ahead and ask questions.
Hello, yeah. Yann, very nice talk. Yeah, second time today we see each other. I have a question regarding this, the dynamics. Of course, you are probing dynamics in Raman measurements. Huh? Can you say something about the, let's say, electron and holes in the system? This iron selenium is like compensated metal. So can you say something about how you can distinguish between different phenomena that you see? Let's say the fluctuations on one side from magnetic fluctuations versus the orbital fluctuations and the charges. Can you maybe say something about it?
Okay, so this is more like a matter of interpretation. So as I mentioned at the beginning of my talk, let me just show you this. So if you look at the Raman spectrum of iron selenium, it has these two components. So you see there is this low energy component that I highlighted in red, that we believe is really associated to itinerant carriers. But you see there is some structure at higher energy that is much less critical, and we believe it's associated more to local spin physics. So there seem to be some, and this sort of two-component response is relatively unique to iron selenide. This is not something that we see in barium 122. So our interpretation is that it's sort of a signature of this dual physics, both itinerant and localized character of iron selenide. But one important thing is that this broader feature is not critical. So if it's really associated to local spins, it's not driving the nematic transition temperature. But it's very robust. It's seen at all sulfur content. So it's pervasive in the phase diagram.
Okay. Thank you very much.
The next one is Chimiao.
Yeah, so very nice talk. I sort of had a question which may be slightly more general about the S-FESE system. So the place where I have looked at the quantum critical fluctuations carefully is the phosphorus doped barium 122, where the magnetic measurements and elasto-resistant measurements of the pneumatic channel show singular temperature dependencies over a decent temperature range in a sort of similar temperature range. There's a high temperature cutoff, there's a low temperature cutoff, but in the same range, they have some kind of power law singularity. Now, for the sulfur-doped FESE, at which doping would you say either Raman or some other measurements have actually given us some substantial dynamical range in the temperature dependence that looks like quantum critically singular in the sense that have a T naught equal to 0 either in the Curie-Weiss or maybe even some other power law.
Okay, so So one comment I wanted to say about the phosphorus barium 122. So the phosphorus barium 122, from the point of view of thermodynamic measurements and transport, is really the best example where you have well-documented quantum criticality. Whether it's nematic or magnetic, I think it's good to debate. But one thing that is important is that in barium 122 system, actually the bandwidth is larger. So the Fermi pockets are larger. So that the Fermi energy, the effective Fermi energy is larger. And that will push down R node. So that is going to reduce probably the effect of pneumato-elastic coupling.
Okay.
What I said about pneumato-elastic coupling in iron selenide may not necessarily apply to barium. That first comment. I think for iron selenide dot with sulfur, I think the fingerprint of quantum criticality is actually not that obvious, because the transport measurements, they see linear NT behavior, but that actually is in the ordered phase. So the best data that shows linear NT behavior are actually in the ordered phase, which is not what you would expect in the typical QCP scenario. And there is little evidence also of any effective mass enhancement. So it's up for me, I think, in this sulfur iron selenide phase diagram, I think the evidence of quantum criticality is not that solid up to now.
And I think I tend to agree. We had talks by Nigel Hussey and Amalia Codier earlier in the series, and maybe they have slightly different wordings, but I think the data were consistent. But but transport to me is a more sort of harder to interpret. I guess I was more thinking about some, like, you know, Raman is probing some correlation function which we know what it is, and so either that or elasto resistance, something that probes a pneumatic channel or any other channel that, you know, one sees singular behavior in a temperature dependence. So maybe if you go to your let's see, what's that, like 5% or 10%, you say R0 goes to 0?
Yeah, that would be between 5 and 10%.
And do you have a temperature dependence of this Raman-derived susceptibility?
Yeah, so that would correspond to something like the blue here.
Okay, I see. Okay.
But the problem that we have is that the sulfur dependence, the sulfur content at which T0 presumably goes to 0 has a significant TS. So that we cannot access the low temperature disordered phase. So we are sort of cut off by the structural phase transition temperature.
And is that the same statement? Maybe it's a question for Zhonghao. At around 7%, do you see anything like substantial temperature range of singular elasto resistance versus temperature?
We haven't actually. Yeah, go ahead. Yeah. So we haven't measured the sourdough elasto resistance. I think the current available data is from Taka's group, and then I remember he saw some substantial deviation from Curie bias close to that doping. But I will say no, for phosphorus still barium 122, the temperature we see T0 equal to 0 is at the point where TS already go to 0. So, and then the only cutoff is the superconducting temperature. So I guess this is quite different.
In that sense, the analysis from elasto resistance is different.
Sorry, I didn't catch your last question.
No, I thought you said that where T naught goes to 0 is larger than 17%.
No, I didn't say that. I said that for the case of phosphorus still barium 122, no, there is no cutoff by the TS.
For the phosphorus 122 case, but for sulfur you don't have a statement, or you don't?
I don't have a statement. Yeah, I only remember that Taka's data is showing a deviation from Curie bias at a quite high temperature. So.
Okay, so maybe I can ask my question.
Yes, go ahead, Benjamin.
Yeah. So Yann, yeah, good, nice talk. Yeah, so I was curious on the if you compare the sulfur doped iron selenide with the phosphor doped barium 122. So what is the the dynamic range where you actually probe, where you see the susceptibility difference between what we call QA and QB, right? The Q10 and 01, and that's where you see, right? So in the phosphor doped, in sulfur doped iron selenide, it seems to be roughly 10-15 millivolt. I mean, do you have similar data, and what is the energy range where the susceptibility?
Between the barium 1 to 2, so this quasi-elastic peak that I'm focusing on in iron selenide, so the range of energy where it's spread is not so different between iron selenide and barium 1 to 2 systems. So it's essentially below 20 millivolt.
Okay.
In all, it's not terribly system dependent. This part. It's the one that is very specific to iron selenide is this broader feature that I alluded before. This sort of broad peak at 50 millivolt. This is very special to iron selenide. But the red part, the low energy part,
similar.
Of energy range is always below 20 meg, and this is sort of universal if you want.
I see. If you include up to like 70, 80 millivolt for the iron selenide, do you also see similar features, or this feature is gone? The susceptibility goes up and go back down. Is that feature still there, or that's gone? If you analyze data.
At which energy?
I mean, below. Let's say if you analyze this Raman data like you plotted here, say below 80 millivolt. If you compare the susceptibility between A and B, is that, do you still have this Curie-West-like temperature dependence, and then goes below TS?
Between A and B, you mean A and B axis, or?
Yeah, between A and B axis. Yeah, I mean, just very similar. You had a plot, right? Susceptibility goes up and goes down at TC. This basically measures susceptibility difference between Q1 and Q2, right?
I mean, the way we probe is that we don't need to. The polarization that we use, we naturally differentiate between. If you want, we are x squared minus y squared naturally.
Right. So I was just curious, if you include the larger energy range, you still see the similar behavior? Or?
The low and the high energy, you mean?
Yeah.
So the high energy is critical.
I see.
So if you want, if I include in my integral, if I decide to integrate up to, let's say, 250 millivolts.
Yeah.
Full range. There, if I were to do a Curie-Weiss-like analysis, it would further decrease my T node. It would be less critical.
I see.
So the full nematic spectrum actually would be less critical. So if I concentrate on the most critical part, the low energy one, then I get a slightly higher T node. So that's the one I described before.
Okay.
And it's true that you can discuss this. So the rationale for doing that is to say, okay, maybe for the TC enhancement and let's say low energy properties, that's really this low energy part of the nematic fluctuation spectrum that is going to matter. But thermodynamically speaking, I should take the full spectrum. So that's an object to debate, whether you should integrate this high energy part or not.
Okay, thank you.
So next question is from Ilya.
Hi, Yann. Very nice talk. So I have a question. If you look on the STM as a local probe on this system, then you see also that that the surface gets quite disordered also with the sulfur. So due to the sulfur dopant. So I guess that in this analysis also disorder should play a role. So and in general, my understanding is that once you introduce disorder, so the basically the impurity are tried to pin to be a pinpoint for the nematic order. So do I understand this right? That this would in principle increase effectively the coupling to the lattice, and then the second, then in general, what do you see in your Raman experiment? So do disorder play any role? I mean, we know that you could still see the gas one alpha, but it could be due to a different reason because of the difference of the mean free path. So so what can you say from Raman?
So the impact of disorder on the coupling to the lattice, as far as I know, I don't think nobody really studied that. I mean, but it's true that generically it would pin your nematic order. So that's
the way I think studies from Copenhagen group by Brian Anderson, where they see that if you introduce a disorder, it basically pins the nematicity near the impurity. But
what I can tell you, for example, is that in the 1 to 2 systems, so if I compare barium 1 to 2 with cobalt doped strontium 1 to 2, and I study samples where they have the same TS. So cobalt doped strontium 1 to 2 would have a residual resistivity that is much higher, so maybe much more disorder. TS minus T naught is virtually identical. I think from the point of view of this plurivalence analysis, my feeling was that it's not so dependent on disorder. So if you want, the integrated quantity is not so dependent on disorder. Now the line shape, so for example, the width of this quasi-elastic Piquet branching may be affected by disorder. But if you work on integrated quantity, my feeling is that it's not affecting too much.
Okay, thanks.
Right. The next question is from Ming.
Thank you, Yann. So maybe I'm thinking about this in a rather shallow way, but I just wanted to make the connection. So in the R-FESE data for iron selenium, there is an additional temperature scale by which the second electron pocket disappears, which is below TS, on the order of 30-40 K, which seems is on par. I don't know, I haven't thought this through, but this is also the work by Yann, Luke, and Rose, that if you look at in the phase diagram of iron, selenium doped with sulfur, there's also a trend of this line coming down. So I just wonder if that.
Yeah, it's difficult because see the TINA that we extract is really coming from the disordered side, right? So of course, once you cross TS, everything has changed. So for me, it's the coincidence. But okay, you never know. But yeah, I would say it's a coincidence. It's really a property of the tetragonal.
So I guess Chimiao, you also have
maybe
a
just
lab question. Sure.
At the risk of offending my friend Ingenieur, I found that anything R0 that's like above 50%, I find it surprising in the sense that in that case I don't even believe the Landau analysis anymore. But nonetheless, one thing which might be interesting to check, I wonder, is the FETSE 50-50 percent case, where my understanding of Junho's data is that there is a singular temperature dependence in a quantum critical way in the elasto resistivity. So I wonder whether Raman would say for that case.
Yeah, we haven't studied this. I think that there are some data, but not as extensive as the elasto.
It seems to be from a perspective of clarifying anything that's quantum critical in the FE 1-1 systems. That might be a good material to look at, and from Raman from other perspectives as well.
But if I remember well, there was a rotation between B1 and B2, right? So it's right in your elastoresistivity data, there is no change of symmetry of this fluctuations. No.
That happens at the very close to the iron telluride side. So in the 50-50, it's still dominated by B1G in your definition. And then there's also recent work on mapping the phase diagram from the iron selenide side to iron telluride side. And it looks like there's a continuous suppression of the nematic phase transition. And there's actually an enhance of the superconducting critical temperature that is different from the sulfur to iron selenide. So that would be an interesting system to study.
Yeah, I agree.
Thank you.
Right. Are there any more questions? If not, well, thank you Yann again for the beautiful talk. And then you can unshare your screen, and then Heike, if you can share your screen.